We think of the world as being pretty solid, right? I mean, the chair you're sitting on, the floor beneath your feet, it all feels real. But what if I told you all of that? It's mostly an illusion. That everything, and yeah, that includes you, is made of 99.9% empty space. Well, today, we are going to take a journey to uncover the truly shocking emptiness of the atom.
So, what does an atom actually look like? If you're anything like me, you probably have a picture in your head of a tiny little solar system with electrons orbiting a sun-like nucleus. But is that picture even close to right? Well, for a long time, scientists had absolutely no idea, and their journey to find the answer, well, it's one heck of a detective story.
All right, so our detective story kicks off around the turn of the 20th century. A scientist named J.J. Thomson had just discovered this tiny negatively charged particle called the electron, and with that discovery, he took the first big swing at guessing what a whole atom might look like.
He called it the plum pudding model, but honestly, an even better way to picture it is a watermelon. Just imagine the whole fruit is this big ball of positive stuff, and the seeds scattered all through it, those are the tiny negative electrons. It's simple, it's intuitive, and it kind of made sense at the time.
Yeah, but there was a pretty big problem. This model couldn't really explain how all those positive and negative charges perfectly balanced out to make most atoms neutral. But more importantly, it was really just a guess. And it was about to be completely, and I mean completely blown apart by a groundbreaking experiment.
And this brings us to the crucial scene. The year is 1909. We're in Ernest Rutherford's lab, where his team is setting up an experiment that was, no joke, about to change our understanding of reality itself. The whole setup was just brilliantly simple. So first, they had a source that shot out these tiny, positively charged things called alpha particles. It was like a subatomic machine gun. Then, they aimed this beam at a sheet of gold foil that was pounded so thin it was almost see-through. And then, they surrounded the whole thing with a screen that would light up with a little flash wherever a particle hit it. Now think about it. If that watermelon model was right, these little alpha particle bullets should have just blasted straight through the soft pudding of the gold atoms. Maybe they get nudged off course a tiny bit, but that's it. And for the most part, that is exactly what happened. But then, something impossible occurred. A tiny, tiny fraction of the particles bounced almost straight back.
This result was just completely baffling. It made no sense at all. It was like, well, here's how Rutherford himself described his shock. He said it was like you fired a cannonball at a piece of tissue paper, and it bounced back and hit you. I mean, what on earth could possibly be inside those gold atoms that was dense enough to act like a solid wall?
And get this was an unbelievably rare event. We're talking about only 1 in every 8,000 particles bouncing back like that. It wasn't happening often, but the fact that it was happening at all, that was a complete game changer. It meant that watermelon model had to be totally wrong. So, to explain this completely bizarre result, Rutherford realized he had to just throw out the old model and start from scratch. And his conclusion was every bit as shocking as the experiment itself. He came up with a radical new idea. He said the only way a positive alpha particle could bounce back is if it hit something incredibly small, incredibly dense, and also positively charged. He called this the nucleus. All the positive charge and pretty much all the atom's mass were packed into this tiny little point at the center. And the electrons? They were orbiting far, far away.
So what fills that vast, vast space between the tiny nucleus and those distant electrons? The answer is nothing. Absolutely nothing. This was the mind-blowing takeaway from Rutherford's experiment. The atom is 99.9% empty space. To really wrap your head around that scale, just imagine this. If the nucleus of an atom was a single coin sitting on the 50-yard line of a football stadium, the electrons would be like tiny specks of dust whirling around way up in the nosebleed seats. And everything in between? Just empty space.
But you know how it goes in science. In solving one mystery, Rutherford created an even bigger one. His new model was brilliant, but there was one tiny detail. According to the laws of physics as they were understood back then, it was completely impossible. It described an atom that just couldn't exist.
So here's the problem. According to classical physics, any moving electric charge, like an electron, has to give off electromagnetic waves, kind of like a tiny radio antenna. And since moving in a circle is a form of acceleration, that orbiting electron should be constantly radiating away its energy. That would cause it to slow down and spiral right into the nucleus in a fraction of a second.
The implication of this was just staggering. If this was true, every single atom in the entire universe should have collapsed almost instantly. The fact that you and I are here to even talk about this is proof that atoms are stable. So, physics itself had to be wrong about something really, really fundamental.
So who saved the atom from this theoretical death spiral? Well, enter a Danish physicist named Niels Bohr. He came along and proposed a radical, almost crazy idea. What if the normal classical rules of physics just break down at the atomic scale?
Bohr took a brand new idea from this strange new field called quantum mechanics. He basically said that an electron can't orbit just anywhere it wants. No, it's restricted to very specific fixed energy levels. Think of it like a ladder. An electron can be on the first rung, or it can be on the second rung, but it can never exist in the empty space between the rungs.
And this led to a whole new set of rules for the atom. Rule 1. As long as an electron stays in one of these special orbits, it's perfectly stable and it doesn't radiate any energy. It just breaks the old rule. Rule 2. It can instantly jump from one orbit to another, but only by absorbing or emitting a very specific packet of energy. And just like that, the atom was stable again.
With that one quantum leap of imagination, Bohr didn't just save the model of the atom. He basically kicked the door wide open to a revolution in physics that would completely change our understanding of reality itself.
Which brings us right back to our first question, but now it's even weirder, isn't it? If you and me and this entire world are made of atoms that are 99.9% empty space, why does anything feel solid? Why doesn't my hand just pass right through my desk? Well, the answer involves the strange and powerful forces between electrons, but that's a story for another explainer.